Here just I want to show you that how can we may resolve this PS ds cos x into its component, into its horizontal and vertical component, so that we can equate all components of the force. So here this is a theta, so again this component will be equals to PS delta S delta x cos theta, and this component will be, as it is perpendicular, PS delta S delta x sine theta. Here Py is applying on particular interface. I don't want to rewrite all these things, but I just want to show you one this thing, and the second is, as we know that this is a complete triangle, delta S here, this is the theta, this will be equals to delta S cos theta, and it will be delta S sine theta, and it will be equals to delta y, and it will be equals to delta z. So both these things will be utilized in this derivation. The figure is in front of you, so there is no need of this figure. I just want to derive the equation. Okay, the sum of the forces acting along y-axis will be equals to Py delta x and delta z minus the force of PS, which is acting along ds and x with its component of sine theta. On the other hand, we can say that along z-axis, Pz has its positive direction upward, and it is acting along delta y and delta x minus PS delta S and delta x and its cos component, yani that means cos theta, and definitely the weight which was acting on downward, which we can reduce it in the form of a specific weight multiplied by the volume of the body, which is equals to this. So on the other hand, I also tell you that these are the points. This is y equals to dy, and you can see here this is actually delta x and delta s sine theta, and similarly this is x and s sine theta. Here you can put the value of delta y, delta z, and here you can put the value of delta y. So I can write these value in this form, and which is equals to MAY, and here as it is the Z component, it will be equals to MAZ, and we can know that M is equals to nothing, just density multiplied by the volume, and we know that the volume of the body is 1/2 delta X, delta Y, and delta Z. So this equation becomes equals to we can put this value here like rho delta X, delta Y, and delta Z upon 2 multiplied by a Y component. Similarly, in the place of mass, we can write here density multiplied by X, Y, Z over 2 with a Z. I think you can't see these things, so I just want to make sure. Okay, now you can properly see. Now we just end up, these are the common factors, so we took common and cancel out it here, delta X and delta Z. So summation of Fy will be equals to Py minus Ps is equals to rho dy by 2 into Ay. Similarly, if we this specific weight is moved towards the right side of the equation, it becomes positive and it's retained positive. Okay, so the equation can be reduced in this form. Here again you can cancel out dy dx, dy dx, dy dx, and dy dx. The remaining part will be Pz minus Ps, which will be equals to the specific weight Z by 2. It might be taken common as well, plus density Z by 2 and Az. If we are talking about the point body, the point body has a dimensions in which the delta Z has a very minor value, the delta Y again has a very minor value, so all these values tends towards 0. If we want to know what is the pressure available for a point body in a which is totally confined by a liquid, so we put the value of 0 here, and we comes to know that equation 1 here, and this is equation 2, can be simplified as Py minus Ps is equals to 0, which implies that Py is equals to Ps. Similarly, this is equation 1 simplification form, and equation 2 simplification form as will be like Pz minus Ps is equals to 0, which implies that Pz is equals to Ps. So this is the proof that liquid applied pressure always equals to in all direction to a point body. Then we have another derivation, the basic equation of the pressure field. First I want to describe the figure. Let's suppose we have this point and we say that the pressure here is P, and we are saying that along y-axis if we are moving, the change in pressure is denoted by dou P by dou y. Okay, and if we are moving in x-axis, definitely in cross direction, so the change in pressure will be dou P over dou x. And similarly for z-axis we have pressure gradient of dou P over dou z. Let's consider this figure in whiteboard. Just pause it. Okay. This is a box. Here, and I'm saying that this is at this point the pressure is P, and these are the axes. This is y, this is x, and this is z. If I am moving in this direction, the pressure gradient is represented by dou P over dou y. If I am moving in upward direction, the pressure gradient is represented by dou P over dou z. And if we are moving in this direction, simultaneously we can say that dou P over dou x will be the pressure gradient. But here if I see only the interface point of this, although the figure is available to you, so you know that this length is equals to delta y, this length is equals to delta x, and this length is equals to delta z. Okay, if I am talking about the pressure which is applied by the fluid in this part of the body, this is the area, complete area covered by the force. Okay, and I will say that I am going back to this point. That means I need to subtract P minus the pressure gradient in this direction. Okay, so what will be the pressure gradient? Dou P over dou y, and up to how much length I need to go back, as we know that this is delta y, so I am going half of it, so I will multiply this length with the 2. As pressure gradient described that how the pressure is changing with the length, and we know the pressure here is P, and if we going back to this point, so definitely we have to apply pressure gradient along this particular length, so we will find the actual value. And if we talk about talking about the force, so we have to multiply it with the dimensions as well, like delta, this is x, and this is delta z. Similarly for this point, what you have to do is P, and we are moving forward, so we have to plus this pressure gradient and for how much length? For that much length. Okay, and again we have to consider the dimensions, which is x and y, which is applying in that particular surface. On the other hand, if we are talking about how the pressure is exerted in this direction and in this direction, it will be determined by respective way, as I have shown you in the figure, that this is definitely we are moving up to this point. So we will add it this pressure gradient and multiply how much the distance we are move forward or move upward, and this is the area on which this pressure is applied, and this is the downward pressure conditions in which we have subtract out certain amount of pressure. If we simplify the previous equations, like we just take how much change in force or balance out these two forces along y-axis. So what we will get is we have to definitely it is applying in positive y direction, and this force is applying over negative direction. So this is when we add up or find the resultant difference between both these things, both these forces, it will be equals to this complete factor, okay, minus this complete factor. When you subtract out this complete factor, this pressure will cancel out, and it is in negative form. Again, this positive signs reduce into the negative sign, so both these terms are addified. When they add, there is a sign of 2 comes, okay, and this complete balancing force will be equals to minus dou p over dou y, delta x, delta y, and delta z. Similarly, for x and z direction, we will find respective results. Again, I want to remind you, we did not included the weight of the body. We will consider it later on in our derivation. Here we are only including the force which is caused by the pressure of the liquid, okay. So in that the weight is not come on that factor, okay. So again we what I have to define another factor here, which is when we represent a vector, we say that it is equals to delta fx along I direction plus delta fy along j direction plus delta fz along k directions. So we want to know the resultant of this all factors. It becomes, as we know that these are the common values, so I just take common of them, and it will be like minus sign is also common, dou p over dou x along I direction plus dou p over dou y along j direction plus dou p over dou z along k direction, and it is multiplied by all dimensions like delta x, y, and z respectively. Here I need to define a function which we call as del or gradient. And which is equals to, if we have some function variable here, this will be equals to dawa of that over dawa x along I direction, similar variable for y, j direction, z along k direction. So if we see, all these factors are including for pressure, and we can say that this complete factor will be equals to gradient pressure, and we put this in this equation here. So the equation reduce up to delta P, delta X, delta Y, delta Z. So I think it will be now clear for you that how we have reduced it up to this condition. So now we will include the weight factor as well, which is acting so the weight is applying on along k direction, and which is equals to delta x, delta y, and delta z. Okay. If we sum up all the forces acting on the body, so this is the pressure forces and this is the weight force, and it is definitely in the negative direction. So we come up with this simplified form. All these two delta x, delta y and delta z are common in both these things. So what we will do is we will common out these factors. On the other hand, we have F, which is equals to M and A. Then we have to put density and delta X, delta Y and delta Z with acceleration. So it will cancel out delta's values, and your equation will be like this: delta P minus specific weight is equals to rho into A. So this is the general equation of pressure. The second case is that how the pressure varies for when the fluid is at rest. If the fluid is at rest, we comes to know that this is the general equation. I just rub out all these things except this equation. So at rest A is equals to 0, and we know that this K is only acting along Z direction. So this complete factor becomes 0, and delta P is equals to minus specific weight along K axis, or you can say in this direction. On the other hand, this gradient has a x component as well, y component as well, and z component as well. So how can it possible that is equal to a factor which has only a single directions like k factors? So we can simplify that dou p over dou x is equals to 0, dou p over dou y is equals to 0, and minus dou p over dou z is equals to the specific weight. This is the general equation for a fluid at rest. Now there are two conditions. If the fluid is compressible or the fluid is incompressible, because this specific weight is equals to rho into g. G is, although is constant, but for compressible fluid, with the changing in the pressure, the density changes. For incompressible fluid, the density won't change. So you have two consequences here. So we will derive the equation first for compressible fluid. Incompressible, let's say, is simple. Dou p over dou z is equals to a specific weight, and we will integrate it. Dou p into minus a specific weight of from P1 to P2, from Z1 to Z2. I think I have represent the figures in the presentation. So you will get P2 minus P1 will be equals to minus a specific weight of Z2 minus Z1, or we can say that P1 minus P2 is equals to Z2 minus Z1, or you can place Z2 minus Z1 as H, which is the height of the column. So this equation is for incompressible fluid, although for compressible fluid we know that their densities will change with the application of pressure, or we can say that their densities is a function of pressure. So we will reduce it in the density form, and we know that PV is equals to nRT and rho is equals to P over molecular weight over RT. This is the equation we will use to resolve the density. So dou P over dou Z will be equals to P molecular weight over RT multiplied by G. This P will move in this direction. Integral of P1 to P2, 1 over P dou P is equals to integral of P molecular weight on R T and G from Z1 to Z2 dz. So it becomes ln P2 over P1. This minus sign will retain here. And if we say that temperature is constant, so we will come up with a solution that molecular weight G over R T Z2 minus Z1 with a minus sign. Okay, so this is the solution. Or in some books you will find that there is no molecular weight is present, so they wrote R bar in such a manner that R is equals to R bar is equals to R divided by molecular weight. So don't confuse with that, whether you are resolving it including molecular weight or not including molecular weight. Whatever the matter is, your result will be same. So this is the general equation for the fluid at rest, and then this is the general equation for incompressible fluid like water, liquids, and for compressible fluid you have to use this relation. Here again I write this equation, and this R is equals to 8314 value divided by the molecular weight. So I did not write the molecular weight here, but this R is not the R of general gas equation. Actually this R is equals to the general gas equation divided by the molecular weight of the gas. Then we have this numerical, which is very simple.